Good afternoon, everyone, and welcome to the fifth session of this IASI event week. This afternoon, on behalf of my colleagues, I will share our work with you on the evaluation of the IASI convective parameters and our experiencing with the IASI data and how we were using surface observations to merge the profiles with. So first, sorry, I need to change slide. I would like you to draw here where you come from and what you do. It would be very nice to know a little bit about you, that where you are, and whether you are a forecaster, researcher, trainer, or manager. You can also use some of the tools here. You have a pencil and things like that. Very good. I see forecasters and trainers and others. You in the other, can you maybe type it in the chat box what that means so we know a little bit better? That would be nice. Okay. TSO, yes. Technical Support Officer of EUMeTrain, I guess. Yes. Oh, nice. Very nice. We have a variety of people here and what you are doing. It's good to know. Good to know. So first, I will talk about a little bit about the motivation. If you have attended the previous sessions of the event week, you might have already heard that the third generation of Metasat satellites will have a sounding satellite, MTGS, which will carry infrared sounder, and it will provide sounding data from geo-orbit in 30 minutes over Europe. And the profiles, the retrievals, temperature and humidity profiles will be retrieved in a similar way as it's done with the IASI data. So it would be a very good proxy for IRS, this data. The other part of the motivation that the IASI level 2 Earth data is available within 30 minutes after sensing. If I may add that very often it's available in even less time, sometimes in 10 minutes, 15 minutes, so the timeliness of data is really already there. So both of these things give us a good opportunity to start exploring the data and look into the potential usage. So as you know that the IRS will be a novelty, there is not many sounding instruments on geo-orbits, only the Chinese ones for now. So if we want to use this data from day one, we need to prepare and train ourselves and also the forecasters. And this starts with trying to explore similar data and look into what it can be done. So we have started this work a couple of years ago already. So first, you may already know the global instability indices from the Metasat second generation satellite, the GII. We thought that it might be a good idea to start with the calculation of these indices from the IASI data and see whether it gives us some possibility of usage or how it is. So first we started to calculate these indices in a couple of cases. Then we also asked one of our forecasters whether he thinks what he thinks about this data, and he was telling us that yes, these indices are nice, but we usually use CAPE and other indices. So we started to evaluate and calculate a bunch of indices, different indices, and looked into which one would be better for this data. In the meantime, we also did a consistency comparison of the IASI IASI level 2 with the GII. This was only to see whether the two data sets is consistent with each other or what are the differences. And all this work gave us the indication that yes, this data has a potential, but it needs to be more evaluated and more explored. So we started to routinely calculate these indices each day from all the METOP overpasses. And the group of forecasters here in Hungary in our weather service were daily checking the data and compared it with the forecast and made notes of the performance of the data. This was done during the summer last year. In the meantime, we're also looking into the IASI Level 2 product, which only uses infrared information. But I will not talk about that part. So what do you think? Try to guess and which of these parameters, this was the parameters we evaluated in the first part. And what do you think, which of these was decided to be calculated from the IASI operationally? We only choose, let's say, 5 or 6 of them. So if you would use your pencil and mark which one do you think, which ones you think we decided to calculate. Good. So precipitation water, yes. That's great. Yeah. Lifted index, K index, most unstable cape. Okay, good. Very nice. Okay. Yes, I see a good variety of indices here. Yes. I will show you now which ones we thought would be the best in the first run. You have marked almost most of these in the previous slide. So we decided to calculate the total precipitate per water, the 0 to 3 kilometer relative humidity, the K index, best lifted index, maximum buoyancy, mixed layer cape, and these two lapse rates. So during this talk, I will share with you some of our experience, some of the typical features we have seen in the IASI data. Also, I will show you some examples and how we did the merging of the surface observations and the IASI profiles, and some of the experiences and challenges of this merged product and the future plans. So the first difficulty we have when we start to look into the IASI profiles, that at the time of the METOP overpasses, in most cases, there are no reference data at the time. So usually, at least in Hungary, we have radio sounds in 0 or 12, 0 and 12 UTC, which is in the middle, or the METOP overpasses is in the middle of these two. So what we can do, we can try to rely on that, what happened later at that environment. So if the environment which is described by the IASI is supported by the weather, what was happening later on, then it's very good. If it's not, then probably the IASI was not that good. And what I would like to also mention here, that all the indices which we calculate from the IASI data are exactly, oh, sorry, it's a typo here, are done exactly the same way we calculate the indices from the model data. I think this is very important because you can calculate, let's say, cape in different ways, because you can run the integration in different ways, and that can reflect on the output value. So the first feature I would like to share with you is that the IASI data can reflect the moisture content very well, and you can see moisture boundaries in the data. you can, I'm sure most of you, especially the forecasters, are familiar with the 24-hour microphysics RGB. And when you have darker blue shades on cloud-free area, you have more low-level moisture, and when you have brighter blue shades, then you have less moisture in this area. So here we have the 24-hour microphysics RGB. Here we see there is less moisture. Here we have more moisture. And this is the, oh sorry, I will need to start to use my pointer, otherwise you will not see what I'm talking about. So here, can you see the pointer? Okay, so here you have more moisture. Here you have less moisture. This is well reflected in the IASI data. This is the total precipitable water from the IASI. Here we have more moisture. Here we have less moisture. If we look into the two profiles in this location and this location, then we see that here we have more moisture, and here we have less moisture, so it's a drier environment. So this is very, very reflected in the data. Another example which we have seen comparing with forecast data, that we can see which we call a foot-like shape in the ECMWF data. This is the ECMWF humidity profile in the lowest levels. This is the ECMWF temperature profile, the green one. And the brown one is the IASI temperature and the IASI humidity profile. And we can see that there is this special shape here. It's like a foot on a leg. And this is often missing from the IASI profiles. But we have also seen this feature in radio sound data. So here is an example of the same day from the 12 hours sounding data that we clearly have this foot here. This is we have not seen this in the IASI profile. Okay, another example here. I either jumped, no, okay. So another example here, I'm sorry it somehow got overlaid this profile, but if we have sun glint in the visible spectra, here we have the EVHRR, the microphysics RGB, and here is the sun glint. And it usually have, when we have very large values of uncertainty in the data, then we cannot trust the profile. This is an example of the very high uncertainties of the IASI. Before, I think yesterday afternoon, and also Thomas on Monday has talked about that for each profile there is an average estimation of uncertainty of that profile. And if this or average error is very high, then we cannot trust the profile so much. So in this case, there is a very large average error up to 5-6 kelvins. And here in cloud-free conditions, we can see that this profile is completely unreliable. So this is more for an example of if you have a very large estimated error, then you cannot trust the profile. So what happens if we are looking at frontal cases? So here we have an example with a very strong front and very dry air mass in mid-low layer in the ECMWF and the radio sound data. And the question is if we can see that in the IASI profile. So here we have the 24 hours microphysics RGB from February. Here we have the estimated error for the IASI humidity, or let's say uncertainty of the profiles. Here we have the uncertainty for the temperature profile. Here we have the ECMWF cake. Here we have in the background the ECMWF total precipitable water, and here we have, and on top with these dots, we have the IASI total precipitable water, and here in the bottom, we have the ECMWF K index, and we overlaid the IASI K index on top. So you can see that we have quite large errors in this area for the humidity. For the temperature, not so much. It's almost the same. But also we have very large differences between the K index, between the forecast and the IASI. And the IASI shows a much unstable conditions. And also in the total precipitable water, we have here larger values than we have in the forecast. So this is reflected here. So a question for you, what do you think, which one is more realistic? The ECMWF or the IASI? You can use your pencil or marker or whatever and try to guess which one do you think could be more realistic. Any tips? Yes. Okay, here we have a marker, ECMWF. Anyone else who would like to guess? Okay, ECMWF is said also in the chat box. Okay, someone thinks IASI is more realistic. Okay. Okay, so I will move on and we will look into the profiles for one pixel here. We have the ECMWF profiles in green, air temperature and the humidity, and we have the IASI profiles with brown. The solid line is the temperature and the dashed line or broken line is the humidity. And you can see here in the ECMWF there is a very dry zone, which is missing from the IASI. So if we try to look, and this was around 9 UTC of the day, both of the measurements, or no, the IASI measurements and the ECMWF forecast. So if we look at the radius on data at 12 UTC, we see a clear dry zone in there. So in this case, more realistic that the forecast was right and the IASI data was off a little bit here, or a lot here. So another case where we had a frontal case, this is a less strong front. It's called a dry ramos in the low layer in the ECMWF data, and this is not seen in the IASI profile. If you look at this point and look into the profile, here again we have the ECMWF with green and the IASI with brown. The temperature is the solid line and the humidity is the broken line. And we can see that here in the lower layer, we have a dry zone in the forecast data, which is not really well reflected in the IASI data. So when we have these frontal cases, then we do not see this typical dry ramos in the lower layer. Oh, sorry, I have jumped too much. So this is just this is an unconvective case, so this is a little bit off the topic, but I think it's quite interesting. This is a winter cold pool situation over Hungary. Here we have the 24-hour microphysics RGB with a very low cloud here. Here we have the no-casting soft cloud type. I'm not sure if all of you are familiar with that, but it just says us that this is the very low cloud. And here we have the no-casting sub retrieved cloud top pressure. It says it's 850-700 hectopascal, which is not a very low cloud or up to this retrieval. And here we have the ECMWF total cloudiness. And we are cloud-free in the model. So why I'm showing this? This I show because the no-casting subclass top pressure retrieval uses ECMWF data in the retrieval. So here we look at the two profiles. We have the ECMWF with green. This is the temperature profile. We have the IASI with the brown, and the dashed line, the broken line, is the humidity profile. So the no-casting software for the pressure height retrieval uses different methods in case of thermal inversion. So we saw that here, if I just zoom into the lowest part, you see there is no thermal inversion in the ECMWF temperature profile. This is the green one, but it's clearly something in there in the IASI profile. So let's say the incorrect retrieval of this very low cloud was caused by the use of a profile which was cloud-free and not reflecting this thermal inversion. So using it with the IASI profile might have caused or made a little bit lower cloud top height or cloud top pressure. So moving back to the typical features, the other thing we have experienced that the mixed layer cape we originally chose because we expected it to be more accurate than other kinds of cape. Because as you know, the mixed layer cape starts from an average value of a layer. We use the lowest 100 hectopascal layer, the average of that layer, instead of a single value. So if the very lowest part, I mean if the 2 meter representative 2 meter value in the IASI profile is not good, we still could have some good values above, and that would result us that would have better results. But we experienced that this mixed layer cape usually is strongly underestimated compared to the model. Why it is a problem for us? If this value strongly differs and often from the model, as the forecaster may not trust it. So what is why it is so strongly underestimated? The ECMWF has a boundary layer module which creates a well mixed layer in the lowest 1 kilometer. So it has the humidity profile has a typical shape in the lower layer, which is often not presented in the IASI. And in addition, the IASI humidity often decreases faster in the boundary layer than the forecasted humidity. Another thing that IASI surface humidity is often lower than forecasted, and if we ever reach the humidity over the lowest 100 hectopascal, it is often lower in the IASI data than it is in the forecast data, and this results in an underestimated mixed layer cape. So here we have an example. This is the ECMWF mixed layer cape and the IASI mixed layer cape overlaid. And here in this area, you can see that it is strongly underestimated compared to the model. If you look into this point, look into the profiles, then we have here the lowest part of the profile. For the IASI, this is brown. This is the temperature profile. For the IASI, this is humidity profile for the IASI. The green is for the correspondingly for the ECMWF. So here is with 8 UTC, and here is with 9 UTC. So we can see that this is clearly the clear difference. Later in that stage, the small cumulus has started to grow in this area, so it was supporting the forecasted profile. Here is another example that although that this mixed layer cape usually strongly underestimates the forecast, in extreme unstable situation it can reach even higher values than the model. So here we have the cloud, the HRV cloud RGB, 24 microphysics RGB. We have the best listed index, total precipitable water from the IASI. Here we have the mixed layer cape, and here we have the ECMWF mixed layer cape, and we overlaid the IASI mixed layer cape to see it better. So we can see that it's in this case, it did have almost the same values as the ECMWF. So we were also trying to find cases where we have added value. The question is that it's nice that we can have this data, and this data can reflect some features, and we can see some things in it, but does it have any added value compared to the forecast? So we were looking into cases when we can have some added value, so we can estimate whether it is worth using this data or not. So we only found a couple of cases where we had added value of the data, but we only looked over Hungary, which is a very small country, and we only have a couple of overpasses by the method, which is usually well before the convection is happening, at least for us. So we believe that with a bigger area and more frequent data with IRS will result more interesting cases. So here is one example from 2018 when the forecast had a local total precipitable value maxima here over Croatia, but it was missing from the IASI data. So what happened here, that this was missing here, and several thunderstorms was forming over Croatia, and when they reached or propagated to this area, they started to dissolve. Our colleagues, forecasted colleagues, expected thunderstorm in this area, but almost no thunderstorms formed there, and they didn't really know what was the reason behind that, because they were really waiting storms there to develop, and clearly this less moisture was one of the reasons of that. Another example here we have the 24 hours microphysics RGB. We overlaid the radar image because there was already some convection going on during the time. We have the cloud RGB, and here we have the mixed layer cape, ECMWF, and overlaid the IASI. Here we have the best listed index and then the IASI overlaid, and here we have the total precipitable water and the IASI overlaid, and the lowest humidity in the same time. And we have here in this area one storm already starting, but according to the forecast, the environment is really not supporting that storm. So what is with the IASI? IASI has a steep lapse rate around 750 hectopascal and no inhibition, and also there is some cape here. Our forecasters with the workstation they have, they can customize these profiles, so they can ingest the surface measurement and start to lift the parcel from that. So all the indices will, the workstation recalculate all the indices and also redraws these graphs. And even with the surface measurement, although the instability will be a little bit decreased, the cape, but it's still unstable and it's still supporting the storm. However, the forecast was really not supporting any thunderstorm to form because it has a lot of, or let's say, considerable convective inhibition, much less cape, and also the lapse rate is smaller. So in this case, the IASI was supporting, better supporting the weather than the forecast. So as I have said, that in many cases we experienced the mixed layer cape to be smaller. So we started to looking into how we could, let's say, not fix it, but how we could have some better results of that. So one of the possibilities is to merge the profiles from with surface observations. So here I have cited this paper, which was done by colleagues in the University of Wisconsin. They used the Suomi MPP NUCAPS data and MEDIS surface observation, high resolution observation data, and merged them. They transferred both data sets to the same grid, and then they replaced the surface values with the observation values, and then calculated the cape. We did something similar, but not the same. So one of the ways we can merge the IASI profiles with the surface measurement is what I have said to you, that we can manually interactively do with the built-in tools in our workstation. And the other is that we can do an automatic merging. For this, we interpolated all the surface measurements for a quite fine grid using inverse distance weighting, which takes also into account the topography. For each grid, the stations within 50 kilometers were used. And then we looked into which of these grids are within the IASI ellipse, let's say here. So all of the grids which were inside this ellipse were averaged, the temperature and the dew point, and then we replaced these values in the profile which is corresponding to the 2-meter values, and then we calculated the indices. So here is an example of the interpolated temperature over Hungary. Here we have the dew point, and I overlaid the 2-meter temperature from the profile, the IASI profile, and the dew point from the IASI profile. You can see that there is places where we have quite a big difference. In the dew point, we can have up to 3-degree difference, which is very good, very large. Sorry. So what do you think? Which parameters are mostly affected by this merging from the ones we started to calculate? Okay, best lifted index, very good. Some other tip, more mixed layer cape, yes. Okay, some more tips. Yes. Okay, so moving on. The K-index and both of the lapse rates are not affected by the merging at all, because the surface values are not used in them. the total precipitate per water and the 0 to 3 kilometer mean relative humidity are slightly affected because we only the merging only modifies the surface temperature and humidity. The mixed layer cape is better affected because it is sensitive to the lowest 100 hectopascal. And for the best lifted index, many of you have listed that it is affected by the merging, and yes, you are right. It is either affected or not affected at all. So this is because the best lifted index calculated by lifting the virtual air parcel from several levels inside the lowest hectopascal layer, and the most unstable value is taken. If the most unstable value belongs to the lifted from the elevated level, then the best lifted index is not affected at all by the merging or the surface temperature and humidity. So let's see a couple of examples. Here we have the original IASI level 2, the ML cape calculated from the original data, and in the background the ECMWF. Here we have the best lifted index from the original data, and in the background the ECMWF. And here you have when we use the merging. Please, what you have to ignore the pixels outside of the border, because we are only or mostly using the Hungarian data, so surface data. So the ones outside is not reliable. But anyhow, if I just toggle back and forth, you can see that we get higher instabilities in the best lifted index, and also we get higher instabilities with the mixed layer. So combining these two measurements can improve the indices, which are more dependent on the 2 meter value. And also the mixed layer cape is, as we know, dependent on the lowest 100 hectopascal, and which is the layer which is very often drier than the forecast. So using the most unstable cape when we merge might be a better choice. So here is an example of the most unstable cape, and here you see the mixed layer cape. So another question which we was trying to answer or look into subjectively, how does the station number and the measurement time difference affect the interpolation? Here we have our original interpolation with all the Hungarian stations. Here we use only the ones which are WMO stations. It's clearly, you can see it's a lot less station, but we can see the overall pattern is quite well reflected in this one as well. And here we only use the WMO stations and hourly data. But we found that using hourly data, when we have an overpass, let's say 8:30, and we use the data at 8, that is has a larger effect, because in 20-30 minutes the surface or the 2 meter measurements can differ a lot, especially in summertime, around 9 and 8. So here we can see the effect of the stations. Here we have the mixed layer cape, the best lifted index, the most unstable cape, and here with all stations, here used only the WMO stations, and here only the WMO stations were used and hourly data. And we can see the differences that we have better, let's say, better values when we use all the stations. So during this summer, our forecasters routinely monitored this merged product, and also they looked into the original IASI level 2 Earth product and made let's say a diary about the performance. So one of the feedback was that you may have seen that we didn't include the SIN calculation. It was only visible if they have looked at the profiles, the SIN. So they asked for the SIN calculation, which was added in August. So they were able to look into that after that as well. I have also asked the forecasters to give back their subjective opinion. So here I have listed a couple. Like one of the forecasters said that usually the stable environment is very well captured in the data, and I haven't said that, but I have this, let's say, diary of the notes they have made, and I browsed over that. I didn't have the time to check everything yet, but there are a lot of interesting information there. I need to evaluate and also do many case studies, because there were many cases they marked as interesting, so it would be very nice to look into. Of course, during their shift work, they do not have the time to dig into all the details, especially when something is happening. So that is, or I hope that will be done during autumn and winter time, when we will have more time. One of them also said that the merged EUMeTrain data better describes the instability than the EUMeTrain, the Earth level 2, but very often overestimates this as well, mostly using only for confirmation of the forecast. So this is one of the other ways that the EUMeTrain data can be used, because it is forecast free. It can be used as a confirmation of the forecast. Whether you can trust the forecast because one independent source is saying the same thing, or the two is completely different, and then you know that you may need to pay attention better to that area. Sometimes the merged EUMeTrain indices seem to be better, while other times the original EUMeTrain, and never both. So difficult to rely on one or the other. This is something we really need to explore further to see if we can find some pattern which relates to synoptic situation or other. And another other feedback was that the merged product seems to be better than the one they have tested last year. That was the original the Earth product, but wouldn't base a prognosis on it purely because it's too few overpasses, and we have no information in the afternoon when most of the convection is happening, and we miss the temporal evolution. I hope this will be much better with the IRS. And what we have also experienced that when we have convective inhibition in the Earth EUMeTrain level 2, and we merge it with the Synop, this convective inhibition disappears very often in the merged product, when in the reality it is there. So this is a real challenge to find the balance of this. So our further plans is to further evaluate all the summer cases, making case studies and look into better different synoptic situations, and also try to find a solution for this overestimated instability sometimes in the merged product and the disappearing SIN. We have a couple of ideas we need to explore, but you can see this is a work ongoing, and this is in close cooperation with the forecasters, which I think is very nice because they already know somehow what they can expect from this data, and they see that the work they are doing by looking into this data, it really goes back to the not just to us who calculate the instability indices, but also back to EUMeTrain who is doing the retrieval. So this is a clear interaction between the developers and the forecasters, and I think that that's something we need to focus on. So with that, I would like to thank you, and if there are any questions, I would be happy to answer if I can.